Hey. Good morning, everybody. Last time we discussed different techniques to control robot manipulators. We saw first how we can control them in joint space. So when we want the robot to track a reference motion that is defined directly in joint space, that's the easiest case. And then we moved to a more complex setting, which is tracking a reference trajectory in Cartesian space. There we saw that we can project the robot dynamics from joint space where it is naturally defined into Cartesian space. And then we can basically treat the problem in the same way as we did in joint space. But then we also discussed the fact that when you're controlling the robot in Cartesian space, your robot might be redundant with respect to that space, because the number of degrees of freedom that are needed to perform that task in Cartesian space might be less than the number of joints of the robot, which is the number of degrees of freedom of the robot. And so in that case, when you have redundancy, you need to add an extra term to your control law in order to stabilize the motion of the system in joint space. Otherwise, that could lead to instability in joint space, and well, that doesn't work in practice. So I left you last time with this exercise to prove the equivalence between two versions of the Cartesian space control law. One version would be this one here. So this control law here, where we are using a simplified version of the main controller, that one that is tracking the motion in Cartesian space, because here we are compensating for the bias forces, so Coriolis, centrifugal, and gravity torques directly in joint space. So this is simplified with respect to the first one that we derived, which was this one, where you can see that the compensation of those forces happen also in Cartesian space. And then since we have this simplified law here, I told you that in the null space task, tau1 can be defined in this way without the compensation of the bias forces, because those are already compensated for in the other term. So this is one option for writing down the complete controller, Cartesian plus joint space. And the other option was instead this one. So you use the standard controller for the Cartesian space, where you have the Cartesian space compensation of the bias forces. But then if you do that in your joint space torques, you need also to compensate for the bias forces H. Okay, you have these two options basically. And I asked you if you were able to prove as an exercise that these two options are actually equivalent, almost equivalent. There is a small difference. Did anyone manage? Of course not. Okay. So when someone will manage, they can come to me, show me how they did it, and then I'll give you the solution. Until nobody does it, I don't give you the solution. I think it's a good motivation for you to do it. And if nobody does it until the end of the course, well, I'm going to ask you this at the exam course. Okay, before we move on to the new subjects, I'm going to show you some plots regarding this Cartesian space controller. So I obtained these plots in simulation using the model of this robot, which is called UR5. We have a couple of these robots in the lab upstairs. I don't know, maybe some of you have seen them. So the controller, well, we only saw one kind of Cartesian space controller, which is this operational space controller. Of course, there exists also other kinds of Cartesian space controller, which I'm not gonna discuss because, well, it would take too much, and that's not the main focus of this class. So I think one of them is enough. The focus here is on the gains that I use for tuning the controller. You remember in the motion control law, we have this term here, which defines the desired accelerations for the end effector of the robot. And those accelerations are computed based on feedback. We have proportional feedback and derivative feedback, PD. And these two gains are very important for the resulting behavior of the system. So higher gains typically is going to result in a better tracking, but also a much more stiff robot behavior. And if we set them too large, typically that's resulting in an unstable behavior. So we are usually limited by the control frequency of our controller and how high we can set them. So in this case, we start with a, I would say, quite small value because kp equal 1 is a small value. For kg, this is a trick that we use very often. We set the derivative gain equal to 2 square root of the proportional gain. This is not by chance. This comes from an analysis of basically a double integrator dynamics. And this is the value of the derivative gain that gives you a critically damped behavior. So you reach the target without overshooting and without taking more time than you need. So it's really a sweet spot of the derivative gain. So first thing, what happens if you don't have a postural task? So you don't take care of the redundancy? Well, it doesn't work. Basically, the tracking, you can see it's very bad from the very beginning of the motion. And at a certain point, it becomes really unstable. And at this point, the simulation basically breaks down because you start getting not numbers, which means that your robot kind of exploded. You reach values that are so high that they cannot be represented by your computer. So postural tasks, very useful in practice. With postural tasks, we can see immediately the behavior is much, much better. Notice that we are starting with a tracking error. So I'm not starting on the trajectory that I want to track. So it's reasonable that it takes a little while to converge that trajectory. But I would say that in this case, it's taking way too long because after 6 seconds, here I still haven't converged to the reference. So the error is probably being reduced, but it seems basically constant. It's behaving better on the x-axis because we can see that by the end of the simulation, the tracking error is relatively small. So here, the first thing I would do is to increase the gain to see if that helps getting on the trajectory faster. So with a gain of 10, which is still not very large, immediately we can see that we are able to get on the reference trajectory within the time frame of the simulation. On the 3 axes, the same happens. So this is a quite good behavior. Now, if I start introducing modeling errors in my simulator, which is always a good idea to test the robustness of your controller. And I think that here by modeling error, what I did was to change a bit the inertial parameters of the robot. So the masses, the center of mass, the inertia tensors, inertia matrices of every link. I slightly modified them. And we can see that, yeah, we have a tracking error even after 6 seconds. Because basically the model that is used for controlling the system is not the real model that is used for simulating the system. And this mismatch leads to an error. How would you try to combat this error? Yeah, you could add an integral term in the feedback. That could be an idea. I don't think I did that. I think I simply increased the gain again, which is a bit more brute force. But as long as you can increase the gain without leading to vibrations or unstable behavior, it's a viable option. And indeed, in this case, that kind of worked, at least for the tracking on X and Y. For the tracking on Z, we can see that it's probably better than, much better than before. Before we had a 20 centimeter error. Now we have a 1 centimeter error. So it's much better, still not perfect. And I think in this case, your idea would be really the solution. If we wanted to also compensate for this 1 centimeter error. If it's a constant error, steady state constant error, integral is really the best solution because it works very well for this constant error. For dynamic errors, it's a bit harder because it has this averaging effect that doesn't work well if your reference motion is constantly changing. But since on the z-axis, the reference is actually fixed, it would work very well. Here I'm adding Coulomb friction at the joints, as we did last time for the joint space controller. And we can see that even the Coulomb friction, of course, has these effects of worsening the tracking. And again, we can recognize the typical behavior. We have this stick and slip behavior. So in this phase of motion, we are in the stick phase. So we are not able to overcome the Coulomb friction. Then we reach a torque that is high enough to overcome the Coulomb friction. And so there is motion. And then again, stick, slip, stick, slip, as we were seeing last time in joint space. As usual, I increase the gain to try to compensate even for this extra modeling error. It works. We can still see here, especially the stick and slip. You see, we have these phases of stick and then slip, stick. Okay, that was the last slide. Of course, one word of advice, Kp equal 1000 is a pretty large gain. I think I've never used it on a real robot. Typically, you're much more in the range between 10 and 100 for feedback gains on a real machine. So in simulations, this works fine because you're in simulation. And so things are much nicer than on the real hardware. Probably again, this high on the real robot would result in very strong vibrations. Okay, because you have certain effects that are not simulated, like delays or sensor noise, which we don't have here, sensor discretization. So the encoders have a finite precision. So you have all these kind of extra inaccuracies that might lead to oscillations, vibration, or in worst case, even instability. So the robot really crashes against the wall. So you want to be really careful when you play with the gains on a real system. In simulation, of course, you're free to crash the robot how many times you want. Any question on this? Now I'm showing you the plots just to give you an idea. Right after we have seen the math, we see a bit the behavior of the system that we can expect to be coming out of that math. Pretty soon we're going to start with the lab sessions. So we're going to implement these different control laws in simulation, and you're going to be able to play with them yourself. Okay, we can then start the new subject, which is QP-based reactive control, where QP stands for quadratic programming. So this is, in a certain sense, the first real subject of this class, because what we have discussed so far is mainly review of stuff that you have already seen in other courses, or let's say classic methods that are not the main focus of this course. This is instead the first real subject, because we're going to start to do control using quadratic programming, which is a special class of optimization problems. Okay, so there are optimization problems with a quadratic cost and possibly linear constraints. We're going to start as usual from the problem of joint space control. Then we're going to do a review of convex optimization. And then we're going to move to task space control, which is a generalization of Cartesian space control. And then we're going to see how the same methodology can be used to control different kinds of robots beyond robot manipulators. For instance, underactuated robots. So like vehicles or legged robots or aerial robots. And then we're going to see how we can start also including contacts into the control framework, because so far we are assuming the robot is not making contact with the environment. When it's making contact, also the controller needs to account for those contacts. And finally, we're going to discuss multitask control. So when you want the robot to perform several tasks at the same time. So a lot of math on this slide, but we're going to take it little by little. And actually, we are starting from something that we have already seen, which is simple joint space inverse dynamics. So this is one of the controllers that we have seen for controlling the robot in joint space. We know that this is the dynamics of the robot in joint space, mq double dot plus h equal tau, nothing new there. And I'm just refreshing your memory. What is the joint space control problem? We are given a reference trajectory in joint space, QR, and we want to find the joint torques, tau, such that the joint angles, Q, roughly track QR. That's the problem, and we have already seen that a possible solution is given by this simple control law. So we set the joint torques equal to m times q double dot desired plus h, where q double dot desired is defined by a PD feedback control. So we have the reference acceleration plus derivative gain times the tracking error in velocity plus proportional gain times tracking error in position. Nothing new here, just reviewing something we have already seen. The new part is coming after. So what I'm going to show you right now is this optimization problem here. And I'm introducing this problem to show you that we can obtain exactly the same control law as above by solving this optimization problem. So it's completely useless because we already know the solution, it's the one above. But just to give you a different perspective, which then we are going to build on top of. So this optimization problem looks like that. We have the joint torques and the joint accelerations as decision variables of the problem. So these are two vectors, and those are going to be our decision variables. So the solver is going to find the value for these two vectors. The cost function that we want to minimize is a quadratic cost function, which measures the difference in norm between the real accelerations of the robot in joint space and the desired accelerations in joint space, where the desired are defined like this. And then we have also some constraints. So subject to, and then everything that comes after subject to are constraints. You can have as many as you want. And the constraints are simply the robot dynamics. Yeah.
2 means it's squared.
Yeah, this is a squared. And this norm here, I didn't specify it, but it's a 2 norm. Indeed, you can rewrite this in this form. You simply take this quantity here, transpose, and you multiply it times itself. Because this is a vector, and the cost function needs to be a scalar value. So if you multiply the vector transpose times itself, you get a scalar. It's a dot product between 2 vectors. And you can see that it is quadratic because it's actually composed of 3 terms. This term here is quadratic because you're multiplying q double dot times itself. So you're getting every element of the vector to the power of 2, and you're summing them all together. This quantity here is linear because q double dot desired is a constant. It's not a decision variable. So the only decision variable you have here is q double dot. So this term here is linear. And this term here is a constant because it's q double dot desired transpose times q double dot desired are both constants, so the product is a constant. So you can neglect it because since you're minimizing this quantity, having a constant sum to it doesn't change the minimization process. It's useless to add a constant to a cost function in an optimization problem. At least mathematically. Then numerically, it could have a little effect, but that's minor. What about the constraints? So we said that the cost function is quadratic. What about the constraints? Are they quadratic as well?
Linear.
Why are they linear?
There are the R part. There's only one Q dot, the other things are all there. And then it's are all constants, so it's Q dot dot plus H equals R, which is linear function.
Yeah, it's a linear function because my variables are q double dot and tau. And so this expression is linear with respect to q double dot and tau. This might be a bit tricky because I told you, if you remember, that this dynamics equation is a nonlinear dynamics. But it's nonlinear with respect to q and q dot, which are the state of the robot. But if q and q dot are fixed, which they are in this context, because you measure them, and then you know them, they are fixed, they are constant values, then this dynamics, if you express it with respect to these variables, it's linear. Okay. So in general, it's a nonlinear dynamical system or a robot manipulator, but its dynamics has this special structure which makes it linear with respect to the accelerations and the torques. And we're going to see later, it's also linear with respect to the contact forces. So when you have in physical interaction, the force enters linearly in the dynamics. And this is actually the reason why we can do this kind of control in a very effective way. Because since we have quadratic cost and linear constraints, then this optimization problem is not a general nonlinear program, but it's a quadratic program. And that's very good news because it's a very simple kind of optimization problem to solve. Okay, why is the solution of this problem equal to the joint space inverse dynamics that we saw last time? I think it's pretty simple to show it. We start from the cost function. The cost function clearly has its minimum at 0. Yeah, it's a quadratic, it cannot be lower than 0. And you attain that minimum when q double dot is equal to q double dot desired. So of course, if we want to reach the minimum of the cost, neglecting the constraint for a moment, we want to set q double dot equal to q double dot desired. If we do that, Then the constraint admits only one solution, because if q double dot is equal to q double dot desired, then tau must be equal to, well, mq double dot desired plus h. So the constraints are satisfied. So it's a trivial problem actually to solve. You can just, by looking at it and reasoning, you can find the solution. And this solution happens to be exactly the same as the joint space inverse dynamics that we saw last time.
In this case, I don't believe that
No, the gains are embedded inside q double dot desired. They're here. Was that the question? Yeah, the gains are always inside the desired acceleration. So you always need them. If you don't have feedback gains, then basically your robot is not going to be able to react to perturbations, modeling errors, anything. So it's not going to work at all, the controller. We need feedback. It's the only way, no, it's not the only way the robot uses the sensor data, because they're also used for computing M and H, for instance. But if you don't have the feedback gains, well, we saw in the plots what happens. If the feedback gains are very small, this happens. That basically the tracking error doesn't go to zero in a reasonable amount of time. If they are zero, it will never go to zero, the tracking error. So I didn't try, but we can try first time that we implement this. Set the feedback gains to zero, you will see it's not going to work. Okay, so we have this alternative way of thinking about the inverse dynamics control problem, which is writing it down as an optimization problem. Then in theory, we could pass this problem to a solver and let the solver do the math, do the computation for finding the solution. This would be pretty useless because we already know the solution of that problem, but the advantage of having this new viewpoint is that now we can augment the problem with all sorts of new constraints. So for instance, we could add inequality constraints inside the optimization problem that say that my joint torques have to be bounded between certain values, which is a physical constraint. The motors of your robots don't have infinite torque. And so it's really useful if your controller is aware of those limitations and can take them into account when deciding what torques you want to apply. Why can we add that? Well, because also this constraint is linear. They are simple bounds, so they are linear constraints. We can also account for current limits, because current in electric motors is proportional to torque. So current is proportional to torque. I wrote it here on the side. This constant k tau depends, of course, on your motor, and you can typically find them in the data sheet of the motors. And so you can write current limits in this way, because what you get here is a linear function of the joint torques. So again, linear constraints. And you can also add another kind of constraints, which are joint velocity limits. So electric motors have bounded torque, and they also have bounded velocity. And that you can read it in the data sheet. Velocity constraints are a bit trickier to add, because velocity is not a decision variable of the problem. You only have torques and accelerations. However, the trick that we use for the velocity constraints is to basically express the next velocity as a function of the acceleration. So assuming q double dot, so the acceleration remains constant during the time step, which is a very reasonable assumption because the time step is typically very small. So the acceleration is not going to change much in 1 millisecond. Then you can express the velocity at the next time step, so q dot at time t plus delta t, as the current velocity, which you know, because you measured it or you estimated it, plus delta t times the acceleration. So you basically integrate the acceleration over one time step, and you get the new velocity. And then you add the constraint on the new velocity, which is exactly what I'm doing here. I'm saying the velocity that I will have at the next control loop, I want it to be within the bounds. Typically, q dot mean and q dot max are the same with a minus in front. And again, very important, this constraint is linear because my variables are q double dot, and this expression is linear with respect to q double dot. So these are all linear constraints that I can add. And so now this optimization problem is no longer trivial. I cannot give you the solution of this problem in a closed form. We need to rely on numerical techniques in general to find a solution. So we're going to need to basically use a numerical solver inside our control loop. We're going to simply pass basically this problem formulation to our numerical solver. The solver is going to give us back some numbers, which are going to be the joint torques and the joint accelerations. Actually, the joint accelerations, we are not going to use them. We are simply going to take the joint torques and we're going to send them to the motors. So that's how an optimization-based controller works. And then we're going to repeat this process at every iteration. And we're going to get basically almost for free a controller that is much more powerful than what we started from. Because now our controller knows that the robot has bounded torques, has bounded currents, has bounded velocities, and it's not going to violate these constraints while tracking the trajectory that we are asking it to track. Okay, so this actually is going to be a recurrent theme. I'm going to repeat this at least 10 times in this couple of months. The main advantage of optimization-based control is that you can account for limits, like physical limits of your machine. These are just a few examples of some physical limits that we have in our machine. Over the next few weeks, we're going to see many more examples. And that's something that you couldn't do before the advent of optimization, of numerical optimization. So we need to thank the fact that we have good optimization algorithms and we have powerful computational machines on board of our robots that can solve this optimization problem extremely fast. So that's why in the 80s, there was no research on this because they didn't have the machine to solve this problem sufficiently fast. So even if there were a few people who were doing research on that, they were considered crazy because, yeah, you have these fancy optimization problems, but you cannot solve them in practice, so your research is useless. Well, that changed over time. Now it would be crazy not to use them. Now, a small parenthesis on joint position limits. Actually, not so small. I want to give this some time because I think it's important and we're going to come back to this later. You've noticed that before I only covered joint velocity limits, but of course, every robot has also joint position limits. I mean, even as we have joint position limits, I cannot bend my elbow or extend my elbow more than this. So ideally, I would also like to account for that physical limitation inside my controller. because if I don't, then my controller could end up making the joint hit the joint stop, which could damage it physically. However, for joint position limits, it's much harder to ensure that they are satisfied than it is for joint velocities and joint torques. So one could be tempted to use the same approach that we use for the joint velocities, because the situation might seem very similar. So what we did for the joint velocities was, well, let's use the accelerations to predict the next joint velocities, and then we add the bounds on the next value. And we could do the same for the joint positions, which would result in basically this expression here. If I assume that my accelerations are constant, then I can predict the next joint positions using this expression here. So I have the current joint positions plus delta t times the current joint velocities plus delta t squared over 2 times the accelerations, which are supposed to remain constants over the time step. It's a parabolic motion. Okay, it's like I'm taking q double dot and I'm integrating it twice, and I get this expression here. And then I could add this inequality constraint inside my QP, my quadratic program. And this is feasible in the sense that it's a linear constraint again, because this part here is a constant. You know it. This term is also constant. And here I have q double dot, which is my decision variable. And so this expression is linear with respect to my decision variables. So technically, I could do it. In practice, it's not going to work. And to explain you better why this is not going to work, I've actually prepared some new material. Which should also be already in the shared folder. So let me switch. Okay. Can you see it? Is big enough? It should be fine. Okay, so basically here I'm repeating myself. I'm going to do some numerical tests to show you why this approach doesn't work. So in this numerical test, I'm going to simulate the robot as if it was a simple double integrator. So I'm setting the joint accelerations, and I'm integrating them twice to get the new joint positions, and I'm integrating them once to get the new joint velocities. So this is basically the math that is implemented inside the simulator. It's very simple. And I'm going to assume that the robot has some joint bounds, Q min and Q max, and some acceleration bounds, Q double dot min, Q double dot max. You could also have joint velocity bounds, but actually for these examples, they don't matter. So I'm going to neglect them in the implementation. So I'm going to simulate a single joint because it's enough to show you the problem. It's not going to be a real full robot with 6 or 7 degrees of freedom. It's going to be just a single joint. And I'm going to do first a simulation applying the maximum acceleration, so q double dot max, for the whole duration, which I think is 1 second probably. So here it is the code that I wrote. Well, I'm importing NumPy, which is a library for doing linear algebra, which I've already shown you. Matplotlib is a library just for plotting stuff. And with this line, I'm enabling the grids in the plots. Then I'm going to define some constant values. So n is going to be the number of time steps of the simulation, which is 100. dt is the time step duration in seconds. So this is 10 milliseconds. So I'm going to do 100 steps of 10 milliseconds, which means 1 second of simulation total. And I'm going to assume that my maximum joint position is Qmax equal 1. and my maximum joint acceleration is q double dot max equal 3. So for q double dot, I'm using the symbol ddq in the code. So it stands for dot dot q. Then I'm going to create 3 NumPy arrays of length n for containing the trajectories that I'm going to simulate. And I'm going to do that for the joint positions q, the joint accelerations velocities dq, and the joint accelerations ddq. The joint accelerations, I'm immediately setting them equal to ddq max, because I'm creating a vector filled with ones, and then I'm scaling it times ddq max. So it's going to be filled with basically 3 in this case. Is everything okay so far? And this is basically the simulation. So I've implemented a for loop for n-1 steps. And at every iteration of this for, I'm simply computing the new joint positions and the new joint velocities based on this vector of joint accelerations, which are actually going to be constants. Then I've written this function for plotting the trajectories. It's not very interesting, but I just reported it here in case you want to use this code and play with it. So it's simply doing the plots. And the plots that I obtain in this case are the following ones. So we can see in the first plot the joint position, which is starting from 0, and it's growing beyond the joint limit, which is 1. The joint velocity is growing linearly, of course, because we have a constant acceleration. And the acceleration is constant, because we set it to be a constant. So we start from a violation of the joint position limits, and now we want to see how we can change the joint acceleration so that we don't violate that limit anymore. So let's try to implement basically the strategies that I just described to you. So we can predict what the next joint position would be by using this expression. So we get q prediction, which is equal simply, to the integration of the acceleration. And then we check if this predicted value is below the joint limit, so below q max. And if that's the case, what can we do? Well, if that's the case, it means everything is good. So we just apply the standard acceleration. If that's not the case, what would you do? What is a very reasonable choice for the acceleration if you detect that you have this risk of hitting the joint limit? Even better? Minus q double dot max. Yeah. Well, if you see that there is a wall in front of you and you risk bumping into it, you brake. Okay, so you decelerate as fast as you can. So that's exactly what we're going to do. We're going to set q double dot equal to minus q double dot max. So we brake as much as possible. And if that doesn't work, it means, well, there is nothing better that we could have done at that moment. So we implement it. The code is very similar to what we had before. The only difference are basically these 3 lines inside the for loop, which do exactly what we just described. So we compute the prediction for what the next joint position will be. And then we check, is this prediction above q max? If yes, we set the acceleration to minus q double dot max. Otherwise, we just keep going. Okay, very simple. These are the resulting trajectories. So first, we can see it didn't work. We are still violating the joint position limit. However, we can see that something did happen, because we can see that here the velocity started to decrease. It didn't continue to grow linearly. So clearly the code worked in a certain sense, because the controller at this point in time, around 0.8 seconds, it started breaking. You can see the acceleration went from the maximum value 3 to its minimum value -3. So why didn't it work?
So it hits the wall, then
Well, it first breaks, then it hits the wall, and then it keeps breaking because, well, in this case, there is no wall in the simulation. Okay, so said otherwise, the problem is that it started breaking too late. You cannot wait until you are at 1 centimeter from the wall to start breaking, unless you have a very, very powerful break, which in this case, it was not available. So you need to basically predict in advance when you're gonna hit the wall and start breaking early enough. So a strategy that has been proposed in the literature to try to solve this problem is to use a larger value of the time step delta t when you do the prediction for the next joint position. In this way, you're not predicting what your position is going to be in one time step, but longer into the future. Okay, so you're kind of increasing your prediction window to a longer time into the future. So for instance, we could give it a try using a time step which is 10 times larger. So instead of predicting in 10 milliseconds where we're going to be, we can predict in 100 milliseconds where we're going to be. So the code is basically the same. The only difference is that here I'm not using dt, I'm using dt pred, which is this value that I've set, in this case, equal to 10 times dt. Very minor change. So if I run this code again, I can see it didn't work. I'm still violating the joint position limits, but something changed because now the robot didn't start breaking at 0.8, but it started roughly at 0.7. So there was kind of the effect that we wanted, just not enough. So we can keep trying. What about 30 time steps? Yeah, we can try it. Well, the code is the same. We just increase to 30, the prediction window. And in this case, it works. And we can see that it starts breaking around 0.5. And indeed, in this case, we are fine. So the robot stops before hitting the joint position limit. However, what's the problem with this approach?
there's no guarantees.
Yeah, it's so-called heuristic. So there are some parameters that you need to tune. There is no exact way to tune it. You need to do it by trial and error. And the value, this value like 30 that we found, it works for this specific case. But if you change the joint limit, if you change the acceleration limit, it's not gonna work. You will need to retune it every time. And also, you're kind of limiting in possibly a very harsh way the capabilities of your robots, because now you can see that the joint didn't even get close to the limit. It stops way before. So it's probably too high, 30. Maybe with 20 we would get a better behavior, but we will need to find the right value by trial and error. So it's not really an ideal kind of method. And at this point of the course, actually, I cannot give you a much better solution than this, but this is just going to be a recurring thing we're going to come back to later on, about 1 month, when we're going to study optimal control and model predictive control, because with those tools, we're going to be able to solve this problem in a much better way. But now, since we are doing the so-called reactive control methods, this is something that is very hard to address with reactive control methods because it requires this prediction window into the future to anticipate when it is the right moment to start braking to avoid something bad happening a long time into the future. Okay, this is instead a reactive controller, so it only looks at what happens right now or at the next time step. So it's very short-sighted. Not now. Okay. I think it's a good moment now to take a break, even if it's a bit early. So I'll see you back here at 35. So joint position limits, you can try to account for them using this expression here, but we saw it's not going to work well in general. And you might need to tune this value here for the prediction of the future joint position to make it work for your specific case. Let's now take a step back and let's start talking a bit about the more general subjects of convex optimization. Because solving optimization problems is something that we're going to need to do a lot in this class. Not only in this part, but also in the coming modules on optimal control and reinforcement learning. So there are in particular these two kinds of convex optimization problems that are very useful for reactive control, which are least square programs and quadratic programs. So least square programs are problems that have only linear constraints, so constraints that take this form here. They can be either equality constraints, so with an equal sign, or inequality constraints with a less than or equal to sign. You cannot have strictly less. It's only less than or equal to. Of course, you can also have greater than or equal to. You just flip the sign of the two sides and you get the other. And the cost function must take this form. So it must be the squared norm of a linear function. So inside the norm, you have something which is linear. Then you take the norm to the power of 2, and it becomes quadratic, which is exactly the shape we had before when we were doing joint space control. Quadratic programs are a more general class of optimization problems which contain least square programs. So least square programs, said otherwise, is a special case of a quadratic program. So in a QP or a quadratic program, we have, again, linear equality or inequality constraints as above. The difference is in the form of the cost function, because the cost function in a quadratic program can take this shape here, which is a general quadratic function, but with the constraint that's the Hessian, so the matrix which defines the quadratic form, must be positive semi-definite, which means its eigenvalues must be greater than or equal to 0. If you don't have this condition, then the program is not convex. And convexity is typically very important, an important property for an optimization problem, because it means that basically we have efficient algorithms for solving this problem. And these problems also have a unique minimizer. So when you find a local optimum, well, that's also going to be the global optimum, because there is only one local minimizer. In a certain sense, they are like easy problems to solve numerically. So good news is for both LSP and QPs, we have very efficient numerical solvers that are available online. Many of them are open source or at least free, so you can download them and use them for free without paying anything. And what do I mean when I say they are efficient? I mean that you can solve the kind of optimization problems that we want to solve in less than 1 millisecond. So we are going to solve problems of like a small size, between 10 and 100 variables. Those problems, you can solve them in less than 1 millisecond with a good solver. And that's very fast, which means we can use them inside the control loop. We can have a very high frequency controller, so like 1 kilohertz, which solves an optimization problem at every millisecond. Okay, that's excellent news for us. Actually, yeah, you can solve it not only on like simple robots like manipulators. You can do this stuff even on humanoid robots at these high control frequencies. So maybe on a humanoid robot, 1 millisecond is going to be tough. Maybe it's going to take 2 milliseconds, but you're still very close to that kind of frequency. So let's see a bit more how these problems are solved and are formulated. And let's focus first on least square programs, which are actually the kind of programs that we will need to solve. So in a least square program, we said the cost function takes this form here. So it's a linear function and you compute the norm and then you take the square. So if you write the square norm with the product between the vector and its transpose, then you get this expression here. That's the same thing we did before for the special case where the cost function was q double dot minus q double dot desired. Now we are doing it for the more general case of an arbitrary linear expression. So we get this form. So this part here is constant because B is a constant. So B transpose B is just a scalar constant value. This part is linear in X. And this part here is the quadratic part. And the Hessian of this quadratic form is this matrix A transpose A. And the good news is that this matrix is semi-positive definite always, because it's given by the product of a matrix times its transpose. And so we know that structurally that results in a matrix which is always semi-positive definite. And maybe you don't know much about semi-positive definite matrices. So let me tell you something more. If a matrix H is semi-positive definite, that's equivalent to saying that Y transpose H Y is going to be greater than or equal to 0 for every Y. So if you take the matrix, you multiply it on the left and on the right times a vector, whatever vector you want, the result is always going to be non-negative. That's exactly equivalent to saying that the matrix is semi-positive definite. And actually, now that I gave you this alternative definition, you can also figure out why the matrix A transpose A is always semi-positive definite. Because I can write X transpose AX as this. Those two are exactly equal. And of course, now you can see why that's always going to be non-negative, because it's actually a square. So it cannot be negative. Okay, so basically by taking this form of cost function, which is the least square function, we know for sure that we are going to get a convex quadratic cost, because the Hessian matrix is always semi-positive definite. So for sure the problem is convex. We don't need to check anything about the values that we use for the problem. Now let's talk about how we solve this problem if we didn't have any constraints. So let's start from the simplest case. We just want to minimize this function. We don't have constraints. Well, when you want to find the minimizer of a function, you might, I guess you all have already seen this. A possible strategy is to try to find a point where the gradient of the function is 0. Because if you're at a minimum, then the gradient must be 0. That's a necessary condition. It's not sufficient, but it's necessary. So the gradient of this function, which I'm calling f, I simply need to take the derivative of this expression here. The last term is a constant, so it doesn't matter. Well, this guy here is quadratic, so when I take the derivative, I get a linear function, which is that. And this guy here is linear, so when I take the derivative, I get a constant, which is that. Of course, here I'm working with derivatives of matrix vector expressions, so it's a bit more complicated than the usual derivative of scalar functions, which I guess you're all more familiar with. So when you take derivatives, you have some vectors that you get to transpose. Some weird stuff happens, but it all checks out in the end. One way to check if your math is correct is to do a dimensionality check. Like this gradient should be a column vector. So what we get here is, this is a square matrix times a column vector gives you a column vector. So that's correct in terms of dimensionality. This part here, you might be surprised because here it was B transpose A, now it became A transpose B. Why? Well, in terms of dimensionality, this is the correct shape because you have a matrix times a column vector, which gives you a column vector. If instead you were using this, so A transpose, B transpose A, B transpose is a row vector, and you multiply times a matrix, you get a row vector. So it wouldn't check out in terms of dimensions. So this expression here gives me the gradient of the function f, and I want this to be equal to 0 to be at a minimum. So I set it equal to 0. This is basically a linear system of equations, which is the only system of equations that basically we know how to solve. So how can we solve this? Well, it depends. It depends. Now we need to enter into the details of the matrix A. So if this matrix A transpose A is invertible, then the solution of this system of equation is pretty trivial. It's simply given by this. I move A transpose B on the right-hand side, and then I invert the matrix A transpose A, and I get the solution. That's the simplest case. This matrix here that we get, that is pre-multiplying B, turns out to be a pseudo-inverse of the matrix A. If you remember, we have already discussed the concept of pseudo-inverse last time when we discussed Cartesian-space control. So you should remember. Why is this a left pseudo-inverse? Well, if you take this matrix and you multiply it on the left by A, then you can see that you get the identity. So it's an inverse, but only if you multiply on the left. If you multiply A times that matrix, you don't get the identity. So it works only on one side. It's not a real inverse.
Why is it pseudo? But because you only have one side.
Yeah, it's pseudo because it works only on one side. Or you could say it's pseudo because it's the closest approximation to an inverse of something that cannot be inverted. Because A is not square. It's a rectangular matrix in general. So an inverse of A doesn't exist in general. So the closest thing to an inverse that you can compute is a pseudo-inverse. And in this specific case, it happens to act as an inverse when you do the multiplication on the left. So it's called a left pseudo-inverse. Then, if the matrix A transpose A is not invertible, but the matrix A transpose happens to be invertible, then the solution is going to be obtained by using the right pseudo-inverse instead of the left pseudo-inverse. And the right pseudo-inverse is defined in this way. You can see it's very similar to the left pseudo-inverse. If you don't look at them carefully, they might seem like they are the same thing, but if you look carefully enough, you see that they are different. I can verify that this is indeed the solution of this expression by simply substituting this solution into the expression. So if I take this and I substitute here for x, what I get is the following one. I get A times A transpose times A transpose inverse times B. Then, of course, this and this cancel out because one is the inverse of the other. And so I'm left with B. So AX is equal to B, which means that my objective function, my cost function is equal to 0. Because if AX is equal to B, well, AX minus B is equal to 0. And that's clearly the minimum of that expression. Below, I also computed the value of the gradient of f, just as a sanity check. And if you do the math for the gradient of f, you can see that you get 0 even for the gradient. So both the function and its gradient are 0 by using this solution here. So clearly it is the minimizer of that expression. But now we have covered only two special cases. So first case, if this matrix is invertible. Second case, if that matrix is invertible. What if neither is invertible? Okay, so in this slide, we cover all cases. And it also acts as a summary of what we have seen so far. So we started from this optimization problem. We want to minimize this least square cost function. The solution in general can be written in this form. X is equal to A pseudo-inverse times B, where A pseudo-inverse can be computed in different ways depending on the values of A. So if the matrix A is a full row rank matrix, which means that its rank is equal to the number of rows, then the pseudo-inverse takes this form here. So it's a right pseudo-inverse. If the matrix A instead is full column rank, so its rank is equal to the number of columns, then the pseudo-inverse takes this form, so it's a left pseudo-inverse. If instead, the general case, A is not full rank, so its rank is smaller than the number of rows and the number of columns, because it cannot be higher, then A pseudo-inverse still exists, but you cannot write it down in a like nice compact form as we did here. So you need to rely on numerical methods for computing it. It still exists, mathematically correct, but you cannot compute it simply by relying on matrix multiplication and inversion. It's a bit more convoluted than that. So in practice, actually, the software that you use for computing pseudo-inverses never relies on these expressions. Okay, so they always rely on numerical techniques for evaluating the pseudo-inverse. So it doesn't matter if it's full row rank, full column rank. It's always gonna use the numerical algorithm, which is much more robust to numerical issues, and so it's always gonna work. Period. So we're not gonna care to look at the rank of the matrix A. So a very common way of computing the pseudo-inverse is to rely on the so-called singular value decomposition, or SVD for short, which I don't know if you have ever heard. Have you heard about singular value decomposition? Raise your hand. Okay, not too bad, like half of you. And for those of you who haven't, it's a very useful thing, I think, to know. It's a very useful tool to know a bit about numerical linear algebra techniques, because they're very useful in practice, and knowing your way around them can be useful when you're implementing stuff. Okay, so that's of course for solving a least square program without constraints, which is not what we care about. We care about solving the problem when we have constraints. That's much more useful in robotics. But I think it's still good to know that we have this relationship between the least square program and the use of pseudo-inverses, which is going to allow us to draw a connection between the use of the pseudo-inverse we have seen in Cartesian space control last time and the use of least square program for Cartesian space control that I'm going to talk to you about in a moment. Okay. So let's now come back to the topic of doing control using quadratic program. We have already discussed how to do joint space control. Now we want to do instead Cartesian space control. So the Cartesian space control problem is formulated in the following way. We are given a reference trajectory XR, which defines some motion for the end effector of the robot. Can be only the position, or more often it's actually going to be position and orientation. And we want to find the joint torques such that the end effector tracks accurately this reference motion. We're going to start from a couple of things that we know. First of all, if you remember, we know that we have this relationship between the accelerations of the end effector and the accelerations of the joint. So x double dot, which are the end effector accelerations, are equal to j q double dot plus j dot q dot, where j is a Jacobian matrix, q double dot are the joint accelerations, well, and j dot q dot are simply the derivatives of j and q. So we have derived this last time, starting from the fact that we know that x dot is equal to jq dot, and then taking the derivatives of both sides, we got that expression. So this is a fact that we know. And another thing that we can take from last lecture is that we know that to compute the desired accelerations of the end effector, we can rely, as usual, on PD feedback. That's the usual way in which we do feedback control. We compute the tracking error in position, scale it by a constant gain, tracking error in velocity, scale it by another gain, the derivative gain, and we sum everything up with the reference acceleration of the reference motion. That gives us the desired accelerations. So one way in which we could tackle the problem of controlling the robot in Cartesian space is to say, well, I know the relationship between the joints and the effector accelerations. I know what value of accelerations I want for my end effector. So I could simply plug that value in here, and then I would get a system of equations which is linear in Q double dot, and I could try to solve them to compute the joint accelerations that corresponds to my end effector accelerations. And once I know the joint accelerations, well, I simply recover the joint torques using the dynamics of my system. That's also a very simple way to do Cartesian space control, which is different from the one that we saw last time. But actually, you can show that they are equivalent in certain situations. So let's try to do exactly that. We have this linear system of equations. It's not in general an easy system of equations to solve, because we know that the matrix J is not square and it's not invertible. So we cannot simply invert J. But now we have this new tool in our hands, which is the pseudo-inverse. So we can try to solve it with the pseudo-inverse. So that's exactly what I did here. I solved for Q double dot, which now becomes Q double dot desired, equal to J pseudo-inverse times X double dot desired minus J dot Q dot. And then once I have Q double dot desired, I can simply use it here inside my inverse dynamics expression to compute the desired joint torques. So in theory, let's say if I'm lucky with the pseudo-inverse, in a way that I'll define later, applying these joint torques should lead to these accelerations. Okay. What I meant with if I'm lucky with the pseudo-inverse, I meant basically if this system of equation admits a solution, then the pseudo-inverse is going to find that solution for me. There could be cases in which this system of equation doesn't admit a solution. For instance, if your arm is completely straight, you're at the elbow singularity, and if I ask my robot to accelerate the end effector in that direction, there is no solution. That physically, the robot cannot accelerate in that direction. Okay, so in that case, this system of equation is not going to admit a solution, and so I'm not going to get exactly the desired acceleration that I want. But that's a physical limitation of the robot. It's not a problem with the control algorithm. Okay. So as long as I'm going to ask the robot to do something that is physically possible, this algorithm works. So this is basically if I want to use pseudo-inverse and do all the computation manually. But what if instead I want to use an optimization problem, as we did for the joint space case? Well, we can easily adapt what we have seen in joint space to also the Cartesian space. We can write an optimization problem, which looks like that. We have exactly the same decision variables as before, so joint accelerations, joint torques. We have exactly the same constraints as before, which are the dynamics of the robot in joint space. So the only thing we have changed is the cost function. And what is the cost function? Is the difference between the end effector accelerations and the desired end effector accelerations, which is very reasonable. It's exactly the same we did for the joint space, now we are doing it in Cartesian space. It's a bit more convoluted because now to express the Cartesian space accelerations, I need to use that expression, j q double dot plus j dot q dot. Is that a problem in terms of optimization? Is the structure of my optimization problem changed? Or is it still a least square program?
Yes, but it's linear with respect of this division.
Yeah, exactly. It's still a least square program because this is constant. This is constant. And this is linear. Yeah. So we have linear plus constant plus constant. So that's linear.
It's better not to be qualified. What would be
An example of a non-least square program? You know, if I had that's not a least square program because what I have inside the norm is a quadratic form. And so if I take the square of a quadratic, I get an expression that has terms that are to the power of 4. That's just an example, but you can, I mean, anything basically besides that is not going to work. It's very limited. But it happens to be limited to exactly the kind of problems that we need to solve. Okay, so we have, again, a least square program. Well, here I'm just saying that this is actually equivalent to writing that. But I write it directly as a function of q double dot because q double dot is among my decision variables, whereas x double dot is not. Of course, I could also decide to add a new optimization variable, which is x double dot. And then I could write the cost function in this form. But then I would also need to add an extra constraint, which is the following one. Okay, so I could add an extra variable and an extra constraint, but I don't think that would be a good idea because you're just making your problem bigger. So in this case, it would result in a slower computation. But it's completely equivalent, mathematically speaking, just worse in terms of computational performance. And now, if you actually try to solve this problem using the pseudo-inverse, because we know that you can solve a least square program using a pseudo-inverse. We have seen it in the previous slide. You can show that the solution of this problem is exactly this. We can do it because we haven't added the inequality constraints yet. So we have a simple program without inequality constraints. So we can still find the solution by hand using the pseudo-inverse. And you can show that the solution is exactly equal to this. Okay, so we see the connection between, let's say, the analytical solution and the optimization-based solution. And now, of course, since we have this optimization-based expression of the problem, we get the same benefits that we got in joint space. So we can add inequality constraints for the torque limits of the motors, the current limits of the motors, the joint velocity limits, also the joint position limits, even though we know they don't work very well, but still. we could give it a try. Okay, so now we can do also Cartesian space control with this inequality constraints being accounted for. I see you're a bit tired. Is there anything unclear you want to ask me?
Which one's the one that is actually more used?
Between the optimization based or the analytic?
Cartesian-space in the end.
Oh, Cartesian by far. Cartesian, yeah. I just start with the joint space because it's simpler to introduce the idea. The joint space makes a lot of sense if you know in advance exactly the motion that the robot should perform, because it doesn't depend on any perceived information, like perceived data. Like in an industrial setting, the robot has to perform always the same task in the same way. Well, you can basically solve the problem offline. You compute a joint space trajectory, and then you can use joint space control, which has some benefits because, well, it's computationally cheaper, and you never need to worry about your Jacobian becoming singular because you don't have to do any pseudo-inverse. So it's actually going to be better in that sense. But you really need to switch to Cartesian space control whenever you don't know exactly the motion that the robot should perform, because it depends on some factors that are only known at runtime. Like the robot that has to pick up objects coming on a conveyor belt, and the object comes in slightly different positions and orientations at different times. And so you need to really use a camera to perceive the object position and orientation, and then plan, basically start moving. Doing that planning from Cartesian space to joint space and then the control in joint space is more complicated than doing directly the control in Cartesian space. So at that point, you would use Cartesian space control. Actually, now that I think about it, I think I had prepared. Yeah, I have here a couple of examples. So here where they use Cartesian space control for performing some tasks on this robot's arm. So this is not exactly the same kind of Cartesian space controller that I explained to you, but it's very similar. So these are relatively old results. I think this was for a DARPA challenge. You know, the DARPA is a defense organization in the US. They organize these robotics challenges every once in a while. And they had this one, I think, around 2010, 2015, no, 2010. Where it was about a robot autonomously performing some manipulation task. So the robot had to do all of this in a completely autonomous way. This was not in the context of a challenge. But this is, yeah, here the main challenge is that you have a bimanual task. So the robot has to use both hands, which is creating like a closed kinematic chain, which is pretty tricky because you can apply very large internal forces without realizing it, which might end up like breaking the robot or burning a motor if you don't pay attention to that. And all of this requires Cartesian space control because you can clearly see the task is defined in Cartesian space, and you cannot plan it in advance because you don't know in advance exactly, like in this case, where the phone is going to be. you only perceive it online. So you need Cartesian space control. So we still have 15 minutes. So I would suggest we move on. The next extension we're gonna go through is actually nothing too fancy, even though we're gonna add probably a lot of new symbols and math. But conceptually, it should feel very lightweight. Because so far we have discussed joint space control and Cartesian space control. And now we are simply going to generalize the concept of Cartesian space control to the more general concept of task space control. So let me give you some examples to motivate why we need this. Suppose that you have a robot that is more complex than a simple manipulator. The humanoid works very well because it's one of the most complex robots we have. So in that case, maybe you're not only interested in controlling the position of the robot hand, you also want to control other things. For instance, the robot has a camera mounted on its head, and you want the camera to look at what the hands are doing to perceive objects. And so you have a task which is basically controlling the orientation of the camera only. Or if the robot is walking, what you care about for managing its balance is the center of mass position. Because you know that if the center of mass goes too far to the side, then the robot is gonna fall to the side. So the center of mass, again, is something that you want to control, which is not the position of the hand. You want to control the feet of the robot for making it take steps. Again, something a bit different from the position of the end effector. So if we are in one of these situations where we want to control these quantities, which are not exactly an end effector position or orientation, then we need to generalize a bit the concept of Cartesian space control. And this is exactly what task space control does. So I think it's a quite small step, conceptually speaking, but it's one that we need to do. So the way we're going to do it is that, well, so from now on, when I say task, what I mean is a control objective. It's something you would like the robot to do. And we can describe in general a task with a mathematical function, which I'm going to call E for error, that we want to minimize. So it's a very optimization-based way of thinking. We have functions that we want to minimize. We assume that the function E is described by an error between the real value of a certain function, a certain quantity, like the center of mass position, or the camera orientation, or the foot position and orientation, or it could be like the angular momentum of the robot. It could be also quantities that are not really measured in meters or radians. And a reference trajectory for that expression, for that quantity that you would like to track. So mathematically, we can say that E, which is a function of the state x, the control u, and the time t, is the difference between the real value of a quantity, the quantity we call it y, and a reference value for that quantity. Typically, the reference is time varying, whereas the real quantity is not time varying. It depends only on the state and the control. By state x, what I mean is the union of the joint angles q and the joint velocities q dot, whereas the control are simply tau. So the reason I'm using this like double notation for the control is that tau is the physical quantity, so the joint torques, but U is the symbol that is typically used in control theory to represent the control inputs of a system. Okay, so I'm gonna have this double notation depending on the case. So you can notice that this function E does not depend directly on my decision variables of the optimization problems that we saw, which are tau and q double dot, but it depends also on the state of the robot X, which contains q and q dot. So I cannot directly take that function E and use it as a function to minimize in my optimization problem because it doesn't depend on quantities that I can decide. So we need basically to introduce an extra step inside our formulation to transform this into something that can be minimized in my least square program. So that's exactly what we're going to do right now. The key idea that we're going to exploit is to introduce some dynamics for this function E. What do I mean is that since E is something that I cannot control directly, what I can try to do is to control it indirectly by controlling its dynamics. By dynamics, what I mean is either the first derivative or the second derivative of the function. So if I find an expression for the dynamics of E such that the limit of E goes to 0 as time goes to infinity, which is what I want, since E is an error, I want it to go to 0. And the dynamics of E is an affine function of my decision variable of the optimization program, so q double dot and tau, then I'm done. Because I can take this expression for the dynamics and use it as a cost function. Because then it's a cost function that is affine in my decision variable, so I can use it as a cost function. And imposing that dynamics lets the error go to 0, which is what I want eventually to happen. It's a bit abstract, I know, but now we're going to see some examples to make it more concrete. Are we good? Okay, let's say that my velocity, my task function E depends on the robot velocities. So that would be the case, for instance, if you had a velocity reference that you want to track with some parts of the robot's body, or maybe you want to minimize the angular momentum of the robot, which is while it's walking, if it's a humanoid robot. That's a very common thing to do, to minimize the angular momentum, because it turns out that human beings do that while we walk. That's the reason why we swing our arms in this way, alternating with respect to the legs. We do that to minimize the angular momentum, even if we don't know it. It happens to be useful. Okay, so our function E is not going to be, as in the general case, a function of X and U, but it's going to be a function of Q dot. Okay, so it's a special case where E depends only on the joint velocities. It doesn't depend on the joint positions or on the joint torques. So if E is a function of only Q dot, well, and time, of course, because we have the time varying reference, then it means that Y depends only on Q dot, and the reference is, as usual, time dependent. So what I can do to impose some dynamics of E is that I can compute the time derivative of E. So I get E dot equal to Y dot minus Y dot reference. I'm simply taking the time derivative of this. And then, since I want to express this as a function of Q double dot, which is my decision variable of the problem, I can express Y dot in this form here. So here I'm using the chain rule for derivatives. I can differentiate y with respect to q dot and multiply this times the derivative of q dot with respect to time. This is equal to the derivative of y with respect to time. So it's not mathematically correct, but I think in our minds, what we're all doing is this simplification. Okay, it's not correct. I shouldn't do it. I'm going to erase this part from the recording and deny I ever did it, but it happens to work in this case. So this product here is equal to y dot. On the other term, we don't need to change it. It's simply the derivative of a quantity that we know. So we also know its derivative, not a problem there. And now this expression here, we're going to call it J because it's a Jacobian. It's not the same Jacobian that we worked with so far in general. It's a like generalized Jacobian, because actually Jacobian in mathematical terms is simply the derivative of a multi-inputs function. Okay, it's a matrix that contains derivatives. And this expression here, the derivative of q dot with respect to time, well, we all know what the derivative of a velocity is. It's an acceleration. So it's simply q double dot. And so we got exactly what we wanted, an affine function of my decision variables, which are q double dot. So that's good. That's our results. We can take that and we can use it as a cost function in our optimization problem. Now, the only thing that is left for us to do is, okay, E dot is affine, but now we need to decide what value we want E dot to take. And we need to choose the value of E dot so that the error goes to 0. So E must go to 0. So if you have taken any course on basic control theory or system theory or linear differential equations, for that matter, you should know that if you set E dot equal to minus some linear function of E, so like E dot minus KE, where K is just a positive definite matrix, then these dynamics make E go to 0 with an exponential behavior. It exponentially converges to 0. So we get exactly what we wanted. So the limit of E for time going to infinity is going to be equal to 0. So putting these two together, we take the expression for E dot, we take the value that we want E dot to take, and we get this expression here. So that's the like equality constraints that we would like to impose. But instead of imposing it as a constraint, we impose it as a cost function. So what we do is that we simply move everything on one side of the equality, and we get an expression that looks like that. And then this is going to become our cost. Of course, when that cost is minimized, the equality is going to be satisfied, because we know that that cost is minimized when the cost is 0. Why do you think it's better to use it as a cost and not as a constraint? What could go wrong if I set it as a constraint?
Since it is an equality constraint, it limits a lot the space of possibility, and therefore I think it would make the life harder for the solver.
It's true, everything you said is true, but that's not That's not the real reason I was looking for. What is the worst thing that can happen when you try to solve an optimization problem? Yeah, that's the problem turns out to be unfeasible. And of course, feasibility is only a matter of constraints. The cost doesn't matter. So if we set this as a constraint in the problem, which we could do, it's not an issue, we could do it. And then this happens to be unfeasible because the robot is in singularity. So we're asking for an acceleration in a direction where acceleration is not physically possible to achieve. Then the problem is unfeasible, and the solver simply tells us, no solution, sorry, problem unfeasible. And well, if you're doing offline motion planning, okay, no big deal. You modify things a little bit and you try again. If you're doing 1 kilohertz control, what can you do? Nothing. I mean, there's no human in the loop there. So if the problem turns out to be unfeasible, then the controller, the code is probably going to do nothing, unless you, of course, wrote the program so that there is a plan B in case of unfeasibility, but typically that plan B is not ideal. It's a plan B. If instead you work with a cost function, what happens if this is unfeasible? Well, nothing bad, typically. So if you're asking the robot, for instance, to accelerate in a direction where it cannot, well, it's simply not going to do it. But you're still going to get a decent solution for the problem, which is going to make the robot do what you're asking it to do in the best possible way. So maybe it's not going to be able to achieve the task, but that's actually probably your fault because you're asking the system to do something that's physically impossible to do. Okay, so if you're not sure if something is feasible, don't put it as a constraint. Put it as a cost. Much better, especially if you're doing control. So yeah, we take this expression and we put it in the cost function. And I think with that, we run out of time, so we can stop here, and I'll see you on Monday for finishing this.